talk of today. We have Eslam Khalaf from Conditional School.
Thanks for the introduction. Today I'm going to talk about some recent work we have about the nature of the correlated insulator ground state for magic angle twisted bilayer graphene at integer fillings. It's a slightly different topic from all the other talks today, and I'll try to give some introduction to those who are not very familiar with the topic. So this work is in collaboration with Mike Zalatel's group at Berkeley, so with Nick and Shubayo, who are postdocs in Mike Zalatel's group, and from Harvard with Shang Liu, who's a grad student, and with Ashwin Vishnu. The work is motivated by the remarkable discovery 2 years ago that when you put two layers of graphene on top of each other and twist by an angle around 1 degree, you get this whole host of interesting interaction-driven phases like correlated or multi-insulators and superconductors. And a simple way to understand this is that when we place two carbon layers on top of each other with a small angle, we get this so-called Morey pattern, which is a pattern which has much longer wavelength than the microscopic lattice scale. So it's around 50, 60 times larger. And as a result, we get a strong reconstruction of the bands into this so-called mini Brillouin zone. So we have a much smaller Brillouin zone, and then when we study the band structure within this Brillouin zone, we find that this band structure depends very strongly on the angle, and around twist angle of 1 degree, we get a pair of flat bands per spin per value. And as we fill these flat bands, we get all these types of interaction-driven phases, basically since the bandwidth is much smaller, or at least of the same order as interaction. So since we have 2 bands per spin per valley, this means we have a filling that goes between 0 and 8. Typically, we use a charge neutrality point as a reference, so we use a filling to go between -4 and +4. So for example, in this figure, this is the figure from Pablo's group at MIT for the first paper. So they measure the conductance as a function of carrier density controlled by applying the gate voltage. And you see here that there is strong insulating features here, but these are just the ones due to this band structure. So this flat band is isolated by a gap from the bands above and below. So this is a single part of the feature. But the more interesting feature are here. So these 2 insulators at filling -2 and +2 cannot be explained by a single particle feature, and they have to be due to interactions. Another more remarkable thing is that when you actually loop around this, you get superconducting domes that seem to at least hold some resemblance to the superconducting domes in ITC cuprates. In the 2 years since then, there are several groups which have reproduced this data and also extended it in several ways. So one of the earliest was the experiment from Corey Dean and Andrea Young's group, where they showed that by applying pressure, you can tune this magic angle. So you can have the same magic angle phenomenon at an angle of around 1.3. There's also been several groups which had this STM data, and the main take-home message from this data was that also at charge neutrality, you get wider separation of Van Hoff peaks, which indicates some enhanced interaction effects. But the data we'll be mostly interested in is the ones from Dima Efetop's group in Barcelona. And apparently, due to the way he prepares his samples, they are much more uniform and has less strain than other samples. And as a result, he seems to see insulating features at almost all integer fillings, with the most prominent happening at charge neutrality and also at +2 and -2. The charge neutrality peak in particular is in contrast to Pablo's data, which didn't see insulator at charge neutrality. They also seem to see superconductors almost everywhere in the phase diagram. And in this talk, I'm mostly be focused on trying to explain the emergence of these insulators at charge neutrality. And as you'll see that the explanation works very well at even integers, but not odd integers, which is kind of consistent with the fact that even integers have the largest observed gaps. So the theoretical description of twisted bilayer graphene starts with the so-called Itzer-McDonald models, where we basically take the continuum model for graphene, consisting of two Dirac cones at the k and k prime points. We take one for one layer rotated by angle theta half, and one for the other layer rotated by angle minus theta half. And then we couple them through a so-called Morey tunneling. So this tunneling potential is phenomenologically described by two parameters. W0 describes the tunneling between the two layers from the same sublattice, so A to A. And W1 describes the tunneling between two sublayers from opposite sublattices, A to B. And this WR are just Morey potentials. Their potentials have the same periodicity as the Morey lattice. And then in the original model, in this paper, they took W0 to be equal to W1 to be equal to some parameter around 100 MeV. And they found that actually there is a pair of flat bands that appear around the magic angle of 1.05 degrees. We notice here that these flat bands almost touch with the other bands above and below, which seems to contradict the fact that in experiments we see very clear large gaps when the bands are completely filled and completely empty. And I'll get to the explanation of this later. But now let me discuss the symmetries of the model. So the model has several spatial symmetries, like it has the C3 symmetry and a mirror symmetry, which is essentially a C2 symmetry about an axis plane. So this mirror symmetry exchanges sublattice and also layer index. There's also a C2 symmetry that exchanges the sublattice and valley index. And it should be noted that not all these symmetries are symmetries of the microscopic model. So for example, the C2 symmetry is only an emergent symmetry of the continuum. There's also time reversal symmetry, which maps the two valleys to each other. And in the limit of small angles, we come to a very good approximation to think of the two valleys as being completely decoupled, which means we have an internal U2 times U2 symmetry. This can be thought of as U1 charge conservation, and then there's U1 valley charge conservation. Then there is an SU2 spin symmetry in each valley separately, because spin-orbit coupling is very weak in graphene. One very important symmetry that's not as obvious as these symmetries is a particle hole symmetry that emerges at small angles. So if in the previous Hamiltonian we neglect the theta rotation in the Pauli matrices, we actually find that the Hamiltonian has a particle hole symmetry that maps positive energy states to negative energy states, but also positive momenta to negative momenta. And this symmetry also switches sublattice and layer. One important consequence of the existence of both time reversal symmetry and a particle hole symmetry is that the model has a chiral symmetry. So there's a chiral operator that anti-commutes with a single particle Hamiltonian. This chiral operator switches valley, layer, and sublattice, and it also flips energy. Now let me go back to what I discussed earlier about the existence of whether there should be a gap here or not. So in the original model, this assumption was made that the Morey tunneling between the same sublattice or opposite sublattices are the same, but on a closer inspection, it turns out that this assumption is not very accurate. And the reason is due to so-called lattice relaxation effects. When you put two graphene layers on top of each other, there are some regions which have AA stacking, some regions which have AB stacking, but graphene energetically likes to be in AB stack, likes to be Bernal stack. And as a result, the AA regions tend to shrink, and the AB regions tend to expand. And the way to model this in this continuum model is to choose W0 to be smaller than W1, and the realistic value obtained from ab initio calculations is around 0.75. A very interesting limit occurs when we take this lattice relaxation effect to the extreme and consider the limit when we completely kick out this type of coupling. So there is no more tunneling between the same sublattice. This model was was proposed by people in Eichmann's group, by Grisha and others. And the model has several very interesting features. One of them is that the bands become perfectly flat at the magic angle, so mathematically flat. But the other interesting thing is that the model has a sublattice symmetry, because we have killed all of the couplings that connect the same sublattice. The Hamiltonian operator anti-commutes with sigma z operator, or the sublattice operator. But since I've shown you earlier that the model has a chiral symmetry, this is another chiral symmetry, and if we combine two chiral symmetries, we actually get a Z2 unitary symmetry. So there is the model has an extra internal symmetry that it actually flips. Yeah, it flips sublattice, layer, and valley. Furthermore, when we look at the flat bands, since chiral symmetry generally maps positive energy states to negative energy states, for energy states at zero, chiral symmetry acts as a unitary internal symmetry. So it leaves the space of flat bands invariant, which means we can choose the eigenstates of the flat bands to diagonalize this operator. This is very important because it means that in this limit, the flat band wave functions are sublattice polarized. They either live completely on sublattice A or on sublattice B. Furthermore, the wave functions living on sublattice A have one Chern number, and the wave functions living on sublattice B has the opposite Chern number. This gives a very interesting picture for the model that's very similar to two bilayer quantum Hall systems that are related by time reversal symmetry. So we start from a wave function in valley K, sublattice A. Acting with C2, we get a wave function with the same Chern number in valley K prime on sublattice B. And the action of C2T or time reversal gives us the wave functions in the other sublattice and the other valley. And this picture would help us understand what happens when we add interaction. So due to this topological nature of the bands, we'll find that this picture is a better way to understand the problem than attempting to write a real space type binding model or Hubbard type model and trying to understand the physics.
Well, a question. So these non-zero values of the Chern numbers can be justified from the symmetry alone, or for the symmetry of the Berry curvature, for example?
No.
No.
You have to. The point is the fact that you have a Dirac cone that's protected by symmetry is likely related to this. So,
Yes,
so
how?
so
Okay, if the Berry curvature is positive and negative, but if they have to be positive on both cones.
so each cone has two states, and then when you map,
when you have
yeah, so you flip the Berry curvature when you go from one to the other, but you also so time reversal maps the state in valley K polarized at B to a state in valley K prime polarized at B. So these two are related by time reversal. But you can also connect the two valleys by C2, which doesn't break, which doesn't flip the Berry curvature, doesn't flip the Chern. So the reason is that for each value you have two states.
Okay.
With plus and minus Chern. So now we'd like to add the interaction to this model. And for the time being, we will just project everything onto this pair of flat bands, and we neglect the dispersion. So we can write the interaction for any generic repulsive interaction in this form, where we have done a flat band projection. This is a standard procedure in like quantum Hall systems, and the flat band projection is determined by this form factor, which includes the wave functions at different momenta, the overlap of the wave functions at different momenta. A very important observation here is that this interaction has a huge symmetry. It has an enlarged symmetry compared to the original model. So the original model only had U2 times U2 symmetry, but once we neglect dispersion, this chiral symmetry operator becomes like an internal symmetry. So we can, for every generator of this U2 times U2 group, we can also multiply it by C and get a new generator. And if we furthermore assume this chiral limit, we switch off W0, we get another chiral symmetry, and then we can also add another set of generators. And if we combine all of these together, we get actually U4 times U4 internal symmetry. This U4 times U4 internal symmetry has a simple visual interpretation, which is that we have for every valley, now I included also the spin degree of freedom, so for every Chern number, there are 4 bands, and we have the freedom to perform an arbitrary U4 rotation among the states with Chern number +1 or the states with Chern number -1. There's also a more direct way to see it by seeing that these form factors are restricted by symmetries to have this form, which means that any unitary rotation of these operators by a matrix that commutes with sigma z tau z is a symmetry. So this problem relates the twisted bilayer graphene to a more familiar problem, which is a pair of SU4 quantum Hall systems in opposite magnetic fields that are related by time reversal symmetry. And this problem, it's actually known that the ground states are ferromagnets. Of course, here I'm writing that they are generalized ferromagnets because I can start with a general SU4 ferromagnet and then apply any U4 times U4 rotation to get any state I want. For example, if I'm a charge neutrality, I can fill 4 states with the same Chern number to get a state which has Chern number plus or minus 1. This state is invariant under U4 times U4. But I could also pick 3 states here and 1 state here to get a state with Chern number plus minus 2. And then starting from any state, I can apply U4 times U4 rotation to get a manifold state of states. This manifold turned out to be this product of Riemannians. And the same is the case for Chern number 0 states. And also, at half filling, I can do the same. I can get either Chern number plus minus 2 states or Chern number 0 states. For later notation, in order to parameterize these manifolds, we notice that these are all Slater determinant states, so they can be described in terms of some density matrix P, that's just the expectation value of Fermi bilinears, and this density matrix can be written in terms of a matrix order parameter. It's a matrix that squares to 1, has the trace that's related to the filling, and in order for this matrix to minimize the interaction, the condition to be a generalized ferromagnet is that this matrix has to commute with sigma z tau z. So for example, if we want a spin polarized state, this is given by choose the direction of the spin quantizations times the spin Pauli matrices. Valley polarized state is just tau z, and the valley Hall state, which is just a sublattice polarized state. So we fill the Chern number plus bands in K valley and Chern number minus bands in K prime valley. We get the valley Hall state. So now we have this picture, we have this manifold of ground of states, which are all low-lying states when we have this interaction term, and we want to gradually add perturbations, either by breaking this chirality condition or by adding dispersion, and see what states are selected. So first, there's the effect of dispersion. And it should be noted that even if the Bayer model doesn't have any dispersion, when we include interaction and do this projection on the flat band, the dispersion gets renormalized. So we actually get dispersion that's renormalized by interaction, and that's usually of the same order of the interaction. But we find numerically that for the relevant range of parameters, this is still small compared to the interaction, around a factor of 3 or 4 smaller. Due to symmetry, we can restrict the form of dispersion. Actually, it only have the Pauli matrices sigma x and sigma y tau z, which means that in this picture, the dispersion appears as tunneling between quantum Hall layers of opposite Chern number. So it couples bands which have the same spin, the same valley, but opposite sublattice. This means it breaks the U4 to U4 times U4 symmetry down to a single U4. And we can now understand what happens, like what's the effect of this term on the energy on the manifold of low energy states. This can be understood simply by noting that if these 2 layers are full, or if these 2 layers are empty, there is no energy gain from this tunneling term. But if one is full and one is empty, we get the virtual hopping processes that gives us some type of super exchange term that's of the order of h squared over u. For the realistic parameters, when the interaction scale is around 10 to 15 MeVs, this is around 1 to 2 MeVs. So it's some smaller scales, like 1 order of magnitude smaller, and it fits into our picture that we have. We first select a manifold of ground states, and then this is a small splitting among these manifold of states. One remarkable feature is that this type of coupling, like anti-ferromagnetic coupling in this SU4 space, this favors the most trivial or the simplest ferromagnets, the ones where we fill spin up here and here, or the one where we fill the same valley in both cases.
So earlier you said that the U4 cross U4 is a symmetry of the interacting description?
It's the symmetry of the interaction in the chiral limit, in the limit when we switch off the same sublattice hopping. In the next slide, I will show what happens when we switch this back on.
Okay, but even in that limit still, so in that limit you get the dispersion from the interactions.
Yes.
But then, so the Hamiltonian hasn't changed, yet the symmetry has been reduced?
Yes, because this symmetry is only a symmetry of the interaction. So this U4 times U4 symmetry is not the symmetry of the full Hamiltonian. It's a symmetry of the interaction. The interaction alone has an enhanced symmetry because, so this chiral symmetry is an operator that anti-commutes with a single part of the Hamiltonian. So it's not really a symmetry of the Hamiltonian, but it's a symmetry of the space of flat bands.
Okay.
And actually, we can write this condition of energy maximization. So the condition that we benefit maximally from this type of coupling can be written as an algebraic constraint on this order parameter matrix. It's a condition that this order parameter matrix anti-commutes with sigma x. Now we consider the next effect, which is what happens when we take W0 to be the realistic value. I mean, the fact that W0 is 0.75, W1 means it's not really a small perturbation. We cannot just add it perturbatively to the chiral limit. However, we notice that if we compute this sublattice polarization, so the expectation value of this sigma z operator diagonalized and take the largest eigenvalue, we find that this never goes to 0 between W0 equals 0 and 1. And around the realistic value, it's around 40%. So even for the realistic limit, where we switch on this coupling, this Mori hopping between same sublattice, the wave functions still have substantial sublattice polarization. So Chern-number plus wave functions live mostly on sublattice A, and Chern-number minus wave functions live mostly on sublattice B. We can use this observation to actually split the interaction into two pieces. One that has only the form factor coming from same sublattice wave functions, the intra-sublattice form factor, and another that's coming from inter-sublattice form factor. And if we compare the typical scale for this part of the interaction and this part of the interaction, we find again that this is smaller by around a factor of 4. And there's also a generic statement that holds over a wide range of parameters. All these statements don't really depend on the details of the interaction, they just depend on the nature of the wave functions at the magic angle, and that's why they hold generic. This new piece of the interaction breaks the symmetry, the U4 times U4 symmetry, to a different U4 subgroup. So the dispersion broke the U4 times U4 symmetry to one U4 subgroup, and this piece breaks the U4 times U4 to a different U4 subgroup. And these two U4 subgroups, their intersection is actually the physical symmetry, which is U2 times U2. And one other observation is that the dispersion is still approximately sublattice symmetric. Roughly because it's a Dirac dispersion, it's sigma x kx plus sigma y ky, so it still preserves this symmetry, even when we switch on this term. And we notice here that if we want to minimize this part, we can apply the same condition that it's kind of a ferromagnet in some generalized space, and derive some condition on this order parameter matrix that it commutes with sigma y. So this is a summary of what we have for our strategy. We have a large scale of the interaction. It's the main piece of the interaction that contains only these form factors connecting wave functions living on the same sublattice. And this is the largest scale in the problem. It's around 15 to 25 MeVs. Then you have two smaller scales that break this U4 times U4 symmetry to two different U4 subgroups. One of them is the dispersion, and the other is this remaining piece of the interaction. Then, if we assume the limit that H plus is much larger than H and H minus, so in this limit, we can make a precise statement about the ground state. Simply that we want to minimize H plus by enforcing this order parameter matrix to commute with sigma z tau z. If we want to maximize the effect of the antiferromagnetic coupling coming from the dispersion, we want the order parameter to anti-commute with sigma x. And if we want to minimize the effect of the remaining part of the interaction, we want the order parameter to commute with sigma y. If we assume even filling, this gives us a unique ground state. So sigma y, tau x, tau y. This type of ground state is an intervalley coherent order. It's an equal superposition of states on one valley and one sublattice, and states on opposite valley and opposite sublattice. We note that this intervalley coherent state has some very interesting feature, which is that although it breaks time reversal symmetry, it preserves a so-called a new type of time reversal symmetry that combines time reversal with some pi value rotation. Okay. So this new time reversal actually squares to -1, so we call it a Kramer's time reversal. So it's an analog of spinful time reversal, but for valley degree free. And using the same argument, we can find that at all filling, there is no simple Slater determined state that minimizes all of these, so that satisfies all these conditions simultaneously. This argument not only tells us what's the ground state, but it also tells us the energy competition among this manifold flow line states. So when we project this dispersion and the non-symmetric part of the interaction on this ground state manifold, we actually get energy splittings as of order 1 to 2 MeV. And we find, for example, states like the quantum Hall, valley or very polarized state. The competition between them depends on the detail of these energetics. So here we have some numerical Hartree-Fock calculations that verify this. So since these are all Slater determined state, they can be captured within Hartree-Fock. And you can see, for example, that this green line is a valley pole state, and this purple line is a valley polarized state, and they cross as we change the angle or if we change the mole parameters. However, in all cases, this KIVC, Kramer's intervalley coherent order, is always the lowest energy state. Microscopically, what does this state looks like? It breaks time reversal, it breaks valley symmetry, but it preserves a combination of the two. Really, this state, since valley symmetry appears microscopically as translation, this state has microscopic orbital magnetization. So it has a pattern of orbital magnetization on the carbon level that goes between 0 minus some value and plus the same value. This is like a time reversal symmetry breaking variant of Kekulé type distortions. So these distortions also break the microscopic translation, but they preserve time reversal. And this is a variant of the same that has also some loop currents, some spontaneously generated loop currents. And actually, one of the consequences of this Kramer degeneracy can be seen clearly in the spectrum. So if you compute the self-consistent Hartree-Fock spectrum, you'll find that there is a degeneracy at the gamma point and at the endpoint of time reversal. So yeah, this is the end of my talk, and the main take-home message is that starting from this chiral limit and adding the different perturbations, we can find the picture that describes twisted bilayer graphene as two SU4 quantum Hall systems with opposite magnetic fields that are related by time reversal. And then adding the different corrections or small perturbations on top of this, on this ground state manifold. And it actually, at even filling, selects a unique ground state that's an equal superposition of between the two valleys and the two sublattices.
Questions?
So can you go back to the slide? So what is this energy dispersion you're drawing?
Which one?
The lower one, the dash.
The energy dispersion is the self-consistent, the Hartree-Fock self-consistent dispersion given the symmetry broken order. So
which figure is that?
it's a charge neutrality.
So the solid line is the.
The solid line is the non-interacting or non-symmetry broken one. It's the HPN, the Bistertz-McDonald one, and this is the one given the symmetry broken one.
Other questions?
So you generate a huge hard gap.
Yeah, the gap is around 14 mm. Of course, the transport gap is not necessarily determined by this gap, and there's order effects and other effects. But this should be comparable to the STM gap, which is between 13 and 14 mm.
Hold on. Most open questions. Your opinion. Open questions.
Oh, well, I think everything is still open. Well, for example,
What has been
okay, within this approach at least, alt fillings are still, it's unclear what happens at alt fillings, and there is a big question of superconductivity. Like when you do this, what happens? So these are probably the most straightforward open questions. We can also go into more detail with the experimental data and see more.
So you mentioned you can also do -2. Maybe?
Yeah.
So is it similar?
Yeah, so at -2, it's a kind of spin polarized version of this. The thing is, so this IVC order just is what happens at charge neutrality. When you are at half filling, plus or -2, you need also to polarize spin. And in both cases, you still have a manifold of states because you have a U2 times U2 symmetry, and then you need to add these Ohm's coupling terms that break the symmetry down. And it depends on this small symmetry breaking term whether you get just purely spin polarized state or a state that has spin valley locking, so spin up in one valley and spin down in the other valley.
So the gap you estimate is what?
So this gap is for half filling, for charge neutrality. For half filling, the gap would be smaller, but it depends on some details because you have two types of gaps. So you open a gap in. So what happens at half filling is that you flavor polarize. You have let's say 4 pairs of bands, and then you push one of them above the Fermi surface, and then you open a gap in the other. And the gap, the actual gap you get depends on whether the okay, I can draw it, it's easier to draw. So you have something like this, and then you can have the other flavor lying here, or lying here. So in this case, this would be your gap, in that case, this would be your gap. And the indication from our numerics is that actually this is the case. So the gap is to the opposite flavor, not that derived.
I have maybe one quick question. So you showed that with your method you get the IV something grams.
Intervalley coherence. Yeah. IVC.
From the experimental data you showed in the beginning, was it clear that the phase is experimentally?
No, it's not clear. So it's there is a first at charge neutrality there is so only Epitoph sees an insulator. The other people don't see an insulator. This it's likely due to strain, and the strain changes something in this picture that could make the semi-metal more competitive. So that's one thing. But having a direct measure of this is not easy. These microscopic currents are very difficult to measure. But what I can say is that this phase is consistent with the lambda fan they observed. Due to this Kramer's degeneracy, it gives you the right degeneracy. But it's not the unique phase that gives you this degeneracy.
There's no more further questions. Thank Eslam and all speakers today.
Tomorrow 9 a.m. we have a severe subject again.